Greetings and welcome to this 3D Motive comprehensive course on creating a box-pushing puzzle game in the Unity engine. I'm Alan Thorne and I'll be your instructor as we explore how to build a 3D puzzle game every step of the way from start to finish. Throughout this course we'll take an in-depth look at a wide range of Unity features from level design and lighting configuration to inverse kinematics, character animation and also load and save game functionality. In this third part of the course, we'll examine gameplay mechanics by implementing box-pushing controls and exploring collision detection, as well as rigid body physics. In addition, I'll show you how to script with inverse kinematics to align and position the character hands during its pushing motion. And then we'll wrap up things by creating a smoothly rotating third-person camera in chase view. By the end of this part, you'll have absorbed an important arsenal of Unity development concepts that'll come in handy in probably every other Unity project you pursue. So, let's get started. So what I want to consider in this first part of the course is player controls. I want to consider the input for the player so that we can move the character around the level. We began to implement this functionality in the previous part of the course, but now we need to consider it in more depth. So to begin, let me just press play on the toolbar and you can see that we have our character in the scene here. And here we have the character node in the hierarchy panel. If I just expand that node, you can see that I've positioned the camera object as a child of the character so that it follows them as they move through the level. Now right now, if I press the W key on the keyboard, we can move the character forwards by one increment. That is by 2 world units. And the idea is so that we can constrain player movement to the tiles on the floor. Now of course the player hasn't been aligned right now to the correct starting position, so they're not quite as I want them. But if I want to turn the character to walk to the right hand side, for example, or to turn them to move to the left, or even to turn them all the way around and move backwards, I can't do that right now because I have no rotation controls. When I press the A and the D keys on the keyboard, I want to turn the player so they can face a new direction. So we need to implement some rotation controls into here. So I'm going to be tweaking the controls that we have created. We have here in the Assets and Scripts panel, we have the Player Controllers script that you can see here in the Object Inspector, and I can also load that here into MonoDevelop, and we have the Player Controller.C# file which we created in the previous section of the course, and that implements the basic movement controls that we have already, but it's still not enough, it's still not quite what we want. So what I'm going to do now is I'm going to jump back into the MonoDevelop and begin to tweak and change the player controller file to support the character movement that we need. So I'm here in MonoDevelop looking at the player controller.C# file, and what I want to do here is to explain to you some of the changes in the code that I've made to get movement up and running for our player character here. So as we've seen before, we have this basic enumeration at the top of our file, enum for movement here, and it's a C# enumeration which just defines the different states of animation for the player character. And when I scroll down, you can see we have our player state variable which really defines the current state that the player is in, and there is the animcomp.setInteger statement that we've seen before to actually pass values directly to the Mechanim animation graph to control which state is playing. We've seen all of that before. But what I want to pay particular attention to is a new coroutine that I've added here for rotation, which you can see here is called rotate, and it will rotate the character a specified number of degrees around their y-axis. So let me just minimize MonoDevelop here and return to our level. Let's just consider the kind of controls that we need. Because we want to restrict player movement to our general grid that we have here, this horizontal and vertical grid, we want to make sure that the player can only rotate by 90 degrees. So for example, if they move here and they want to turn down here, for example, then we have to rotate them exactly 90 degrees so they can continue along their path in this direction. So it's important to constrain player rotation to 90 degrees. Now to achieve that, if I just bring back MonoDevelop, you will see here that I've added rot increment, and the default value is 90 degrees, and indeed I want to keep it at that. This defines the amount of rotation in degrees that the player should turn on the y-axis when we want to turn to change direction. So if I just minimize MonoDevelop and I scroll up in the hierarchy panel and I select the player character, you can see here in the object inspector for the player controller component that we have rot increment, and it's set to 90 degrees. I also have a property rot time, which determines the amount of time in seconds that it should take the player to rotate 90 degrees. In this case, I specified a value of 0.5, which is half a second. And here we also have move time, which represents the amount of time, again in seconds, that it takes the player to walk forwards by 2 world units. And again here I've specified 0.8, so that is 80% of a second. So I'm just going to bring back MonoDevelop again and take a look at the rotate coroutine that I have added to this source file here. So in this movie, what I want to do is to consider the rotate coroutine that we've coded for the player controller C# file. I'm just going to scroll down. Now it's important, the purpose of this rotate coroutine, when I can find it, there it is at line 68. The purpose of the rotate coroutine is to rotate the player character around the y-axis. It's very similar in fact to the move function because it uses exactly the same logic. It transitions the position or the state of the player from one moment to the next over the rot time in the case of rotation. So for the rotate coroutine, what we do is we begin by getting the Y rotation, the current Y rotation for the player character, using the transform component rotation.eulerangles.y. That gives us the rotation for the player character on the Y axis. And then we calculate the destination rotation that we want to rotate to, which is the current rotation of the player plus the rotation increment, which will be either 90 degrees or negative 90 degrees. This rotate coroutine is called inside the handle input function, which is called every frame to update player input. If I just scroll down to the handle input function, you can see here at the bottom we check player input. If they're pressing the A key on the keyboard, the left key, then we rotate by negative 90. And if they're pressing the right key, which for me is the D key, then we rotate by positive 90 degrees. So I'm going to scroll back up to the rotate coroutine that we have here. And so we calculate the destination rotation that is, and then over the rot time, which is specified here, and for us this is going to be 0.5 seconds, then over that time we interpolate the angle so the player rotates from their current orientation to the destination. And so finally, here at this stage, the rotation is completed. So what I'm going to do now is, with all this code integrated together, I'm going to give it a test in the editor. Remember, if you want to check anything in this source file, it is included in the course companion files inside the playercontroller.c# file. So just open up the Unity project and open up that file and you'll get where you'll need to be. So I'm just going to minimize MonoDevelop now and switch back to the Unity editor and see this code in action. So if I press play on the toolbar and I press the W key on the keyboard, the player walks forwards. And if I press the D key, we rotate to the right. If I press the A key, we rotate to the left. And again, W key moves forwards in the direction that we're looking because we're moving forwards along the forward vector. So again, I can turn left and I can walk forwards, and again walk forwards along this way, rotate this way. And so we've got this sort of player control set up here and it's looking pretty good. But of course, right now the player is not properly constrained to the main game grid. If I just stop playback for a moment and switch to the scene tab, you can see here in the scene, let's just switch to a perspective view, like so. You can see here on the floor, if I select these pieces, we've got one floor tile here and another floor tile here, and the player really is sort of in a nowhere place between them. We want the player to be constrained to these floor tiles in a nice neat grid. So I'm just going to position the player now to a proper starting position. Let's just switch to an orthographic view, maximize the game viewport. Actually, let's just select the player character first. And I'm going to position the player to about here. I'm just going to try and line up their transform gizmo to around about the center of the tile here. So now let's just switch back here to the perspective view, and I think that's looking fine. Let's just press play on the toolbar, and again now the player is constrained to the level grid in nice neat increments. So you can see that he's moving from one tile to the next tile to the next tile and the next one, and we rotate, and we're also constrained to the grid because these are nice neat squares measured 2 by 2 weld units. So that's how, using the move and the rotate function, we can create basic player controls. Next we're going to be considering adding boxes and collision detection, so stay tuned. So now I want to introduce the crate or the boxes into the level. These are the boxes that the player is going to be pushing as they move around the level, pushing onto their destinations, that is. So the crates really are a critical part of this box pushing game. So we can find these inside the meshes folder. They were already imported in the first part of this course. So you can double click the meshes folder and you'll find them inside the props folder. Here, when I can select this box object, here is the crate object we're going to be using. In the preview panel it's presented in a nice bright purple color. So what I'm going to do is drag and drop this box into the scene so you can see it here. And again, it still appears at this bright purple, but we can easily fix that by applying a texture to it. Now the first thing you'll notice over here in the object inspector is that this cube, this box object, has an animator component. Now we are not going to be playing any animations at all on this box, or well, we are going to be animating the box in the sense that the player can push it and move it around the level. But we're not going to be playing any animation data on it using the Mechanim system. So we can remove this animator component completely, and indeed in cases where you don't need any animation at all, I recommend that you remove the animator component from your object. So I'm going to just click on this cog here and choose remove component, and now bam, it's gone. So I'm going to switch over to the materials folder, which you can see here. And the material data for the crate here is not in fact on the prop material, it's on the environment material. So I'm going to drag and drop that onto the crate, and now you can see we've got the texture data applied. And I'm just going to kind of align this, just maximize the viewport here, and use this transform grid to align this cube to roughly the center of the floor tile. So around about there should be fine, like so. So I'm going to arrange it about there. Now the first thing you'll notice here is that perhaps the crate is a bit too small, and in fact it's penetrating through the floor. So we want to just raise this up in the scene here, like so. But it's pretty small, and again we want it to be a little bit larger. So I'm just going to increase the scale on all axes to about 1.5. That should be around about enough, so just raise that cube up onto the floor there, and I think that's looking about right. So that's about the right size for the crate and for the rest that we're going to be using. In general, I'm going to be creating only one crate because we're going to be adding some extra data to this, and I'm going to be creating a prefab from this crate so that all the other crates will simply be instances of that prefab. So you'll see that we've now got a crate in the scene, but if I press play on the toolbar, we've got a problem. First of all, we've got a player character that can just walk through crates. So although I'm walking forwards here, the character is not pushing the crate. But not only that, we've got a character that can also walk through the walls in the level. So long as he's constrained to the grid, he's just walking through the walls. And that really is not what we want. We need to get some proper physics and collision detection in here. So that's an issue that I'm going to be turning to next. Now I want to consider the issue of collision detection. In Unity, whenever we need to detect collisions between any two objects, we need to use collider components. That's the way that Unity handles collision detection. Now there are two main ways we can get collider components onto our objects. One way, for example, if we wanted to get colliders onto the scene environment geometry here, is to go over here to the project panel where it says Assets, Meshes and Environment. We could select any object, for example this corner piece. And again, in the preview panel you'll see that this object is rendered in a bright purple color because it cannot find the appropriate material. But let's not worry about that right now. Over here in the Object Inspector under the Model tab, you will see if we move down the Generate Colliders checkbox, and if we enable that and scroll down and click Apply, Unity will search through the geometry of this mesh and generate colliders dedicated for that mesh. And we could repeat that procedure for all of the others, and that would automatically add collider components to them. But that is a very expensive way, computationally expensive, for generating colliders. It can lead to performance problems. Now, a much more optimized way would be to use the file menu at the top here and choose component and then choose, for example, physics, and use a box collider to simply approximate the scene geometry. That is a much more optimized way, and it's the method that we're going to be using here in this course. Now, I do want to say one thing ahead of time, is that we won't be using colliders to approximate the floor of this scene. The way we're going to be working with colliders is we're not going to be using the standard physics system. We're going to be using the colliders and detecting collisions manually. So I'm just going to be adding colliders for the wall geometry here and for the boxes, but not for the floor. That will not be necessary. So let's get started at adding colliders to our project. So I'm going to start by creating a new game object in the scene. I'm going to move up here to the file menu and choose game object and create empty, or I could press Ctrl-Shift-N on the keyboard, and that creates a new game object which you can see here in the hierarchy panel. Again, it's created it at this world position here, and I don't want that. I want to put this at the world origin, so I can choose the cog icon, and from the menu I'm going to choose reset, and that resets it to the world origin. You can see here it's represented by this gizmo. I'm going to name this object colliders, like so, and you can see the name here listed in the hierarchy panel. And I'm going to be adding some new game objects beneath this as children, and these are going to contain the colliders we'll add to the level. So I'm going to press Ctrl-Shift-N again to add another new object, and I'm just going to parent it to this collider object here. Select this game object and just scroll around until we can find out where it is. Okay, so I'm going to put the collider for a wall piece in this area here. So about there, let's just raise it up here. And I'm going to add a collider component to this. So I'm going to choose from the file menu here, component physics. And I'm going to add a box collider. And you can see now that's been added in the scene. You can see it outlined by these green outlines here. So we've added a box collider. And if that's not visible for you, make sure that it's enabled here, box collider, from that gizmos drop down in the scene viewport. Make sure you have a tick there in box collider so that you can see that in the viewport. If it's not ticked, you won't see them at all, so make sure that's enabled. So we have this box collider, and I'm going to just adjust the size here. So I'm going to adjust, for example, its height to maybe something like that. It doesn't matter that it's a little bit larger than we need. That's absolutely fine. So let's just increase this just a little bit. I'm going to switch to the top viewport, switch to an orthographic view, and just increase the size here to something like this. The Z here to something like that. So now we've approximated the collision data for this whole corner of the level. And I really want to sort of repeat this procedure for the other sides. So I'm going to select this, press Ctrl D on the keyboard to duplicate that and move it over to this side. And again, let's just maximize the viewport here. I'm going to press Ctrl D and bring that down to this side here. And again, Ctrl D to bring that over here. And for these endpoints, if I just come out of the main viewport here and I choose the colliders, you can see all four are now selected. What I want to do again is to duplicate these and add them to the ends here. So one at the end here, one here, one here, and one here. So let's press Ctrl D to duplicate that, bring it in here, and just raise it up to around about there. Again, Ctrl D, bring that down here. Control D again, let's just bring this over to this side and arrange it about there. And again, Control D finally to bring this one over to this side. Now if I select the parent object, the collider's parent, you can see all of the colliders in the scene. And that's looking pretty good. We now have colliders around all of the walls. And I also want to add a collider to the crate object. So let's just go back to the scene here, switch to a perspective view, select this box here in the viewport. Again, notice it doesn't have a collider component attached automatically. We need to add one. So I'm going to move up here to the File menu, choose Component, Physics, and add a box collider component. And it quite nicely sizes this box collider automatically to the mesh to completely contain it and act as a bounding box. So this box collider for the crate here is already sized to exactly the size that we need. And in doing that, I've now added colliders to the scene geometry and the box geometry. We're now ready to move on. So in this movie, I want to consider the general logic that our collision detection is going to take, because we're going to be testing for collisions manually as opposed to relying on the Unity physics system to do it for us. So let's take a look at how exactly the logic is going to work. Let me just select the player character in the hierarchy panel and maximize the game view. Now with the player character, we know that when he moves, or when she moves rather, that she moves in discrete increments. So for example, right now the player character is standing there, but if we walk forwards, we know that we're going to be walking forwards by one tile, at least one tile. So that's 2 units in this direction. This means that when the player presses forwards, we know for sure that the player is going to walk forwards by one tile. And this really offers the key for our collision detection. Because what we want to do is, for example, let's say the player turns and faces the wall. What we want to do is to say, okay, so you want to walk forwards, do you? Right, well, what's in the next space? Let's take, for example, a point in space that's ahead of us on the next space here. And we want to say, okay, if I just select the colliders here, we want to say, okay, well, if the point on the next space is inside a collider, then we can't walk there because it is blocked off. It's marked by this collider and we can't walk there. But of course the player may also walk forwards and there might be a crate there. Now in that case the crate does have a collider, but we want to really test and say, okay, is this a crate? If it is a crate, that means we can push it. But things are not quite so simple, because though the player can push this crate, they can only do it because there's an empty space behind it. If there was another crate here, for example, the player would not be able to push this because they can't push 2 crates at once. They can only push 1 crate at a time. So we need to detect collisions not just for the next space, but also for 2 spaces ahead to see what kind of space is behind a crate if we come across a crate. So the first kind of functionality that we need to implement for collision detection is testing for points. We want to be able to pick up any point in the scene, any point expressed as a vector, an X, Y and Z component, and we want to say, okay, is this point intersecting a collider anywhere? Is this point inside a collider? And we want to get a straightforward answer of yes or no. If, for example, we know that a point is here inside a collider, then we know that the player cannot walk there. So we're going to really start by implementing point testing with colliders. And we're going to be getting started with that next. So now I'm here in MonoDevelop and I want to show you the functionality that I've added for testing points with colliders in the scene to determine the kind of space that we are on. You'll see that it all begins here really with line 13, where we have public enum space state, and 3 states are defined. They are empty, crate and collider, and these determine the kind of states that any space can be in. For example, let me just minimize MonoDevelop and bring up the scene here. For example, if we take this space here, Well, we know that this space is empty. It's empty because we can walk there and there's no crate on the space. So the space is empty. This space here, for example, it is a valid space. It means that we could walk on it if there were no crate there, but it just so happens that right now there is a crate here. So the state of this space is crate. But then we also have the kind of space that's way out here behind the walls. Now this space is a collider space. It means that you can't push a crate onto there and you can't even walk there at all. There's no way that the player can ever reach this area. So these are the three states of any space in the level, and they are described using this space state variable here. Now, of course, I've also coded the point testing functionality further down in this source file using the point state function, and effectively it accepts any vector3 point in the scene and it tests that point to see what kind of space that we are on, and then the output value is a space state description of the space that is defined by this point. So let's see how the point state function works. Now it starts by using a for each loop to cycle through all of the collider components in the scene. We have a collider C in the array colliders. Now let's just scroll up to the top of the class and you will see that I've added a private array variable here of colliders, which is initialized to null, meaning that it begins completely empty. And in the start function at line 67 we say colliders equals object.findObjects of type collider. And what this will do, what this single statement will do, is populate the colliders array with all of the colliders in the scene. That includes the collider attached to the crate. So let me just minimize MonoDevelop and back in the scene here. If I scroll up and select the colliders object, it will include all of these colliders and also the collider on the box mesh. Now to prove this, we can do that easily. I can just move up here and change this variable, the colliders array, from private to public so that we can see it in the object inspector. Let me just move over, select the player character, and here for the player controller component, you can see the colliders variable here is currently in the editor set to size 0. But if I press play on the toolbar to begin playback of the level, you can see that it's automatically populated with 9 different elements. And these are all the colliders in the scene. Element 0, for example, if I select that, that is the crate mesh. And again, these other remaining colliders are for the wall objects that we created previously. So let me just stop playback, switch back to MonoDevelop, change this from public to private, press Ctrl S on the keyboard to save those changes, and scroll back down to the point state function. So we cycle through all of the colliders in the scene, and then what we do is we use the cbounds.contains function, testing it with the point here to determine whether the point intersects any of the colliders in the scene. If the point that we've specified does intersect a collider, then it could be a crate or it could be a wall. We need to test which one it is. So here we're using tags, compare tag, to determine what kind of object the collider is attached to. If this object is marked or tagged as a crate, and I'll show you tags in just a moment, then that means this space contains a crate. If, however, the collider is not associated with a crate, then it means that it must be a wall. So we return space state collider. But of course, if there was no intersection at all with a collider, if it wasn't a crate or a wall, then it must be an empty space. So it's important for this function to work properly that all of the crates in the level are tagged with the crate tag. And we can do that quite easily. Let me just minimize MonoDevelop and select this crate in the scene. You can see that I've already tagged it up here as crate. I just click in this tag field and I select crate. If you don't have the crate tag specified, you can add a new tag. just click in that field, move down to the bottom, choose Add Tag, and then you can add your tag in here. But right now I have tagged this crate here with the crate tag, and that will allow the point state function to work correctly. So that's the basics of testing for points with colliders, but there's still more work to do. In the preceding movie we coded point state functionality to check a point against a collider, and that is just simply one part of the movement mechanics that we are developing for the player. There is still more to do. In particular, we need to implement validation for player movement. Let me just show you what I mean by that. Because right now, although we have the ability to test for any point in the level to see which kind of tile it's on, we still need to have functionality that uses that point testing to work out whether or not the player is allowed to move forwards into a particular space. Right now the player is standing here looking forwards, and the question still remains as to whether or not the player can move there. So for example, right now if the player were standing back here and were to press forwards, we would use the point testing functionality to test for this point here. We would find in fact that the space was empty, and so the player could move forwards into that space. Again, if the player was turned to face in this direction here against the wall, and they were to press the forwards key, the W key on the keyboard, then we would not want to allow them to walk forwards, because the point in the next space would be inside a collider, and that would mean that the player couldn't move there. So we want to just undo those changes there. And finally we have this case here with a box where the player can move forwards. We know that there's a box on this space. In this case we need to also validate the space behind, because if there is a wall there or if there is another crate there, then the player cannot move forwards and push this crate. But if there is an empty space there, then the player can move forwards and push this box with them. So to handle this validation for movement, I need to code a new function, and I'll show you that by returning to MonoDevelop. If I return to MonoDevelop, you can see that I've created a validate walk function, and it returns a type of move type, which we've seen before. It's the enumeration here that specifies whether the player is walking or pushing or is standing idle. So it will return the movement type that is allowed for validating the current movement. So how does this work? Well, first of all, it uses this value here for dest pos, and that gets the position or a vector position for the next space that is forwards in front of the player. So it uses the player's forward direction vector to determine what the next space is, and it gets that represented as a point. And then there's the double dest point, which takes the player's position and gets a point that is 2 spaces away. We will need to get this to test whether or not a crate can be pushed into an empty space. We then determine the status of the next space by using the point state function that we have coded and passing it the destination point here to determine whether the next space is empty, contains a crate, or is a wall. And we do the same procedure here for the space that is 2 spaces away from the user. We then move down and we say, okay, so if the next space is empty, then we can allow a walk there, and we return a type of move type walk. If the next space has a crate and the space behind the crate is empty, then we can push the box, and so we return that type. In all other cases where perhaps there are 2 crates stacked up together, or there is a crate against a wall, or the next space is simply a collider space, we return a type of move type idle, meaning that the player cannot move forwards at all. Movement is forbidden, even if the player is pressing the forwards key on the keyboard. We simply cannot move to that space. This validate walk function is integrated with our handle input function, which we have seen before. Here we have the functionality to code the rotation for the player. But if you take a look at the player movement, particularly the movement forwards, we call on the validate walk function to check whether movement forwards is allowed, and if it is, we then allow walking forwards or pushing the box forwards. So I'm just going to minimize MonoDevelop and test out this functionality now. I'm going to press the play button on the toolbar. Actually, no, I'm not. I'm going to exit this, switch out of the scene tab. I need to be in the game tab. That's important. Always remember to do that. So I'm going to switch to the game tab, maximize the viewport, press play on the toolbar, and now you'll see we can rotate around. I press W on the keyboard and I can't walk through that wall. It's blocking me even though I'm pressing forwards. Again, I can walk forwards and I'm being blocked this way, and again I turn here and walk forwards, I'm being blocked again, and that's because we put those colliders behind the wall. So our point state function is at work. What about in the case of a crate? You notice here we've got a crate, one crate, and there's no crate behind it, so I should be able to push this, and indeed I can. I can keep on pushing it, and notice that now I cannot push it through the wall. What about the case of two of these crates? Well, we can easily just sort of arrange that scenario. I'm just going to select this crate, press Ctrl D to duplicate that, and just move a crate behind it. And now press play on the toolbar and I walk forwards, and I'm not allowed to move this crate now because there's another crate behind it. So the movement validation is now working excellently. But there is a problem. There is still one problem that remains, or an aesthetic problem that remains, and we're going to be considering that next. So now, by using the point state function in combination with the validate walk function, we are able to move boxes around the scene and to honor the position of the colliders. But there is still a problem, an aesthetic problem, and let's take a look at what that is. So I'm going to press play on the toolbar, and I'm just going to push the box forward and press pause on the panel here. So make sure you're pressing pause while the player is pushing the box, as we are here. So let's just switch to the scene tab and have a look at the pause posture here. You will see that the player is pushing this box, but of course their hands are actually nowhere near the box. This phenomenon is not very apparent in the game tab here because of the chase view that we are using, but still the user might expect the player's hands to be slightly higher and for it to look a bit more realistic than this. The player still looks too distant and disconnected from the box. So what we need really is control over the hands, so that we can stretch them out further to push the box and make it look just a bit more realistic. Now, to achieve this, we're going to need to use a feature known as inverse kinematics. But let me show you one thing that won't work. So let me just press stop on the toolbar here, and I'm going to just move out of this main view and move over to the hierarchy panel and dig deep into the skeletal hierarchy of the player character. So I'm going to open up the character here, open up the reference base node, and we get all these nodes that we can see here. But if I dig down further to here, we can find we have our wrist base, which refers to the right wrist of the character. Let's just consider the issue of the right wrist of the character. What I actually want to do is for the character's hands to be on or very near to this box, so it looks more like the character is actually making contact with the box and is pushing it as they move. You might think, well, we could just get a reference to this wrist game object during the game and move it. Well, let's see what happens when we do that. I've got the wrist selected here and I'm just going to move it, and you'll see that what happens is we can really just elongate the arm to quite ridiculous lengths. The player stands in position and this hand really just goes on and on and on, and it doesn't look realistic at all. So let's just put that back by pressing Ctrl Z. You'll see that the problem here is that no matter how much we move this wrist, the rest of the arm does not follow. And that's because here we're not using inverse kinematics. So in the next video I'm going to be considering what inverse kinematics is and how we can get it working in Unity through scripting. So for the next few minutes, what I've done is I've just jumped into Blender, but you could be using any 3D software that you want. And what I want to do here is to demonstrate to you inverse kinematics. And it's easier for me to demonstrate it here than it is in Unity. So I want to show you what inverse kinematics is, how it's important, and say some preliminaries about how we can get that working in Unity. So right now in front of me I've got a rigged bone arrangement of a body here with a thigh, a shin and a foot. So we have a basic kind of single leg arrangement here. Let me just turn off inverse kinematics for the moment. Now without inverse kinematics, if we wanted to move or arrange this leg in a way that we could put it in perhaps a walk-in animation, we would have to animate every single one of these bones manually. So I would have to select this bone and I would just have to rotate it out a little bit, just select this shin here, rotate that out a little bit more, and effectively we are moving from the top of the chain downwards, animating every bone in the leg. And that would be really quite tedious, and the problem that we're experiencing in Unity is we're grabbing something like the wrist or the hand or the foot and we're just dragging that, and it's being dragged completely away from the rest of the skeleton. What we want to do in fact is be able to move this foot and have the rest of the leg automatically change and rotate to accommodate that. We effectively want to say at this joint here, at this particular position here, what we want to do is fix this in place so that every time if we choose to move it, then the rest of the joints in this leg chain here will rotate and bend to accommodate the change. So now I'm just going to switch to this thigh bone, activate inverse kinematics. Now if I select this foot and I move it, you'll see that the rest of the leg bones in the chain, they animate and they rotate to accommodate where I'm moving that foot. And again, even if I move the body here, you can see that the bones and the joints are rotating to accommodate that. That is an example of IK at work, and we want to use this principle here to be able to position the player's hands on the box and have the rest of the joints animated nicely. So let's jump back over to Unity, but before I do that I should mention that in Unity, scripting with IK, which is what we are going to be doing, is a pro-only feature. You need to have the professional version of Unity to do it, which means that if you are using the free version of Unity, you'll have to skip over the remaining IK videos and pick up there at the next section. Okay, so I just wanted to keep that in mind. Let's move on. So to get started using inverse kinematics with the player character to position their hands on the crate, the first thing I'm going to do is create two new empty game objects. So I'm going to switch over here to the File menu and choose Game Object Create Empty, or you could press Ctrl-Shift-N on the keyboard. So I'll press Ctrl-Shift-N and we get a new game object in the scene. I'm just going to reset these transformations here and I'm going to name the object Left Hand Dest for destination. I'm going to duplicate this object and I'm going to call this one Right Hand Destination. So now we have two objects, a left hand and a right hand object. Now I'm going to select the player character. Actually I'm going to fold up the skeletal hierarchy here in the hierarchy panel, and I'm going to drag and drop our hand destinations underneath the player character. Now you'll notice that because these are empty game objects, when I deselect them in the scene, they suddenly disappear. In fact, I can't click anywhere in the scene to reselect them because there's no visible indication that these objects exist. The only way to select these empties is by using this hierarchy panel. I can click on the left hand desk and suddenly you can see the gizmo representation. But there is a kind of a neat little trick that you can do to make these objects easily visible in the scene viewport. I'm going to select the left hand object here. And on this box icon that you can see up here in the Object Inspector, I'm going to click on that and I can choose an icon for this object. So I'm going to choose this diamond shape here. I'm just going to select the diamond shape, and all of a sudden now in the viewport you can see this diamond shape for the object. I'm going to do the same for the right hand object. I'm going to click on the box, choose the sort of diamond shaped icon, and now I can lift up both of these objects in the viewport. And in fact, now if I deselect them, you can just pick them and select them now in the scene, and you no longer need to return to the hierarchy panel. So what am I going to do with these two separate objects? Well, I'm going to use them as destination points for the player's hands. So let's bring in the left hand destination, which refers to this hand here. So I'm going to bring that into view here. I'm going to bring that slightly over here, and I'm going to bring it down perhaps just a little bit. So what I want to say is that when the player character is pushing the box, right now their hands come out to about here. I want her to stretch her hands out maybe to about there, like so. So something like that. That's where I want her hand to be. And obviously when the hands move to that destination point, I want the rest of the arm joints to follow and accommodate that change. I'm going to do something similar with a right hand object. Let's bring this into view around about there-ish and about there. So let's just bring that into view. I want the right hand to be positioned somewhere about there, maybe further down, about there-ish. So I'm using these 2 points here to mark the destination points where I want her hands to be when she's pushing the box. And again, you don't need to worry, just because these objects have icons, you don't need to worry that they'll be visible in the game viewport. They won't be. If I press the play button on the toolbar, you'll see that you can't see them in the viewport at all. So they're only visible in the scene viewport while you are editing the level. So I've marked these left hand and right hand destination points. And these are going to be interacting with the IK that we're going to be creating, and we're going to be seeing that next. So we've now created two empty objects in the scene to mark the destination positions that we expect the hand to move to using inverse kinematics. We expect the hands to move here and to have the elbow joints and the shoulder joints to conform to that position. Now, of course, if I press play on the toolbar, nothing is going to happen because it's not enough just to have these two empty objects in the scene. We have to use scripting and do some extra things. So I've gone ahead and edited the playercontroller.c# file to implement those things, and I just want to bring up MonoDevelop and show you how this works. So let me just bring up MonoDevelop here, and you'll see that the first thing we have for the player controller class is I've added two new public properties. In particular, left-hand dest and right-hand dest. These are both of type transform, and they refer to the different empty objects in the scene that mark the destination points for the hands. We added those in the previous video. So these are just references to those game objects. We can easily specify these by dragging and dropping to the object inspector. So I'm just going to minimize MonoDevelop. Let's come out of the scene view here and select the player character in the hierarchy panel. You'll see that for the player controller object we have the left hand dest and the right hand dest objects already selected. If they weren't here, you could just drag and drop them into the appropriate slots and everything would be assigned correctly. So we've created these two empty game objects to mark the hand destinations here. Let's go back to the MonoDevelop script file, and using inverse kinematics there is a special function or event that you need to implement in your class to work with IK. I'm going to scroll down to the bottom of the player controller source file, and you'll see this function here which is onAnimatorIK. And this is a special event that you can implement, which is going to be called every time that the skeleton needs to recalculate the inverse kinematics. Now what do we have here? Let's take a look at what we've got. We've got the animator component, and these implement these functions: set IK position weight and set IK rotation weight, and set IK position and set IK rotation. We have these two main functions, and what we are doing with these functions, you can see here, is that I'm specifying that I want to use IK with the right hand and also with the left hand, and I want to use the right hand destination objects, the position and the rotation of those objects, to mark the endpoints where the hands should meet. And this parameter here, the 1.0 F, indicates the strength I want the effect to have. If I specified a value of 0, for example, then there would be no IK effect applicable at all, but because I've specified a value of 1, I have specified the default strength for the effect. So if I minimize MonoDevelop and I press the play button on the toolbar, you'll see still that nothing happens. Her arms are by her side, and that is because we need to enable a particular parameter in the animator graph here. So I'm just going to stop playback and switch to the animator graph. You'll see that we have our usual graph that we coded earlier, idle, walk and push. This was implemented in a previous part of the course. I want to pay particular attention to the top left hand side here that says base layer, and there is an arrow there which we can twirl open. And if I scroll down just a little bit, you'll see a checkbox here which says IK pass. You must make sure that this tick box is enabled if you wish to override the inverse kinematics for the character. In this case I do, so I want to enable that checkbox. I'm going to move back to the Game tab and press play on the toolbar. You can see that something here has changed with her hands. I'm going to go back to the scene to have a look, and you can see now her hands are outstretched, but they are rotated. And the reason is because they inherit the rotation of these game objects. If I select the left hand desk, for example, you will see here in the rotation parameter that it's rotated by 90 degrees. If I set that back to 0, the hand is now at the correct rotation, and the same applies for the right hand as well. I'll set that back to 0. So notice that the rotation of the game object also controls the rotation of the hand. Let me just maximize the game viewport so we can see this better. So here again we're rotating the game object, and that's rotating the hand. We can also rotate it up and down, and that controls the rotation of the joint there. That's looking pretty good. I can also select this game object, use the translate tool, and I can start to position this arm, and notice that it's starting to move. Again, I can bring it further back, and notice that the joints now here on the arm, the elbow joint for example, is starting to bend and conform based on our inverse kinematics. So I can come out here and I can start rotating the hand around, and it's looking pretty good. Everything is working quite nicely with this, so I'm just rotating the arm out. I can move it in and out, and well, frankly I can move it all about. It's looking pretty good. So that's the basics of how we can get inverse kinematics up and running. Of course, it's not enough just to have this. We also want the arms to work, again with the box pushing functionality. Right now we can see how the inverse kinematics is working for the arms. It's looking pretty good, but it's still not enough. We must do more. So I'm just going to stop this here. I'm going to select the left hand desk in the viewport, clear out the rotation because I know that's wrong, select the right hand one, clear out the rotation there. This is a good beginning. We just need to go ahead and amend our code in MonoDevelop so that the inverse kinematics applies when the character is pushing the box. So now, without further ado, I've changed the onAnimatorIK function so that now the player character will move their hands towards the box when they are pushing the box. And we can see that here I'm checking the player state, and I'm saying if we are pushing the box, if the move type is .boxPush, and remember this value is assigned earlier during the handle input function when we are validating the walking functionality, whether we are determining if we are pushing a box. So if we are pushing a box, then the standard IK applies. I've chosen a value of 0.5 as opposed to 1.0 to create some blending between the default state and the IK position that I want to use. And if we are not pushing the box, then we enter the else statement, in which case the IK is not being applied. So all of this code now is written in, it's saved. I'm going to minimize MonoDevelop. I've got my scenario set up here in the level, so I'm just going to press the play button on the toolbar, and straight away now you can see the hands are higher up and they are pushing the box. So let's just try that again. You can see, yes, this is working nicely. The IK is now taking effect. If of course we didn't like that position for the hands, all we would have to do would be change the position of the left and right hand destinations, and those hands would move to meet that position. So I can accept these values. We're now ready to move on. Now, of course, no box pushing game would be even remotely complete unless we gave the player the opportunity to successfully complete a level. And in this game, a level is completed when all the boxes have been pushed onto their destination points. Now, right now, we don't have any destination points at all, so we need to correct for that. So what I'm going to be doing to create these destination points is I'm going to be using the Unity 4.3 sprite functionality. What this means in practice is that to follow along with this part, you'll need Unity 4.3 or above, which is the version in which they introduced the 2D functionality. So I'm going to switch over here in the project panel to the textures group, and you can see we have imported an Atlas texture here. I will select that, and in the preview panel you can see we have a level complete texture that we're going to display when a level is completed, but we also have this target texture. I'm going to be using this target texture to display on the floor of the level here to represent the destination points for the boxes. Now, to put this into the level, I'm going to click on this right pointing arrow to expand this group, and I'm going to select the target sprite that we have here and drag and drop that into the hierarchy panel. I'm just going to raise it up so you can start to see this object coming in here, bring it into the level. Now right now this is too large, so I'm going to scale this to 0.3 on all axes. And again, I need to rotate it as well because it should be aligned to the floor. So I'm going to switch to the rotate tool, and yes, we're rotating on the x-axis here. So I'm going to rotate that 90 degrees so that it aligns with the floor. I'm going to switch to a top view, change it to orthographic, maximize the viewport, and bring this destination point over here, aligning the axes, the gizmo axes here with this floor tile. And that looks pretty good. So let's just switch back to a perspective view and maximize the viewport and bring this down to the floor and align it on the surface here. So something like that. That should be pretty close. Now, of course, I want to add some transparency to this sprite. And the way I'm going to do that is create a new material. So I'm going to switch to the materials group, right click, choose create, and I'm going to select material from the list. And I'm just going to call this Spr Matte and select that sprite material. For the shader type, I'm going to select shader, sprites, and default. That appears outside the recording window, but there is an option there that says default, and I'm going to choose that. And straight away we get this default sprite here. And then we've got a tint that we can apply if we wish to apply a tint, but I don't. I'm just going to drag and drop that material onto my sprite here. If I select that in the viewport, you can see we've got a sprite, and you can see the material assigned here. Now, of course, we have a tint. I don't want to give it a particular color tint, but I do want to adjust its transparency. We can do that by clicking on the tint color, and you'll see here in this color picker we have a value for the alpha. I'm just going to reduce the alpha here to something like that. I think that's looking pretty good. It shows us part of the floor and the destination on top of it. So that's looking pretty good. But we also need to know when the box is going to be pushed onto this destination point. And again, to do that, we need to use colliders. So I'm going to move up here to the menu, choose Component Physics, and I'm going to add a box collider. You can see the box collider has been added, but of course I don't like the size that we have. I want to stretch this up even further. So I'm just going to increase the Z size here. Let's just move this box collider to about there. Something like that, so that we can detect a collision between the box and this collider here. I'm going to enable the isTrigger volume here so that we can detect when the box enters. We're not really interested, we don't want this to be detected as a standard collider along with the walls or along with the boxes. We just want this to be a trigger volume. I'm also going to mark this with a tag of end. Again, if you don't have an end tag, I suggest that you create one, but I'm just going to mark this with the tag of end to indicate that this is an end point. And now, having created this, we are really ready to kind of prefab this kind of object. So I can switch over to prefabs, I can choose create, and I can choose prefab. I can mark this as end, like so. Let me just go and correct the spelling there. Should be lowercase n, and I can drag and drop this target onto that endpoint, And now we've got the endpoint that we can just reuse as many times as we need in the level to create endpoints. So off screen, I'm probably going to go ahead and duplicate these endpoints to create 4 end pieces for this level, because I know in advance that we're going to have for this level 4 boxes, which means we're going to need 4 endpoints. So I'm going to pick up endpoint creation and resume in the next video. Now off screen, I've gone ahead and created the remaining destination points for the boxes. But of course right now you'll see that we still have only 1 box, and that is entirely intentional because there is still something else that we need to do regarding these boxes. If I press play on the toolbar and I'm in the scene and I push the box, for example, and then I walk around this side and I push the box onto the destination point, it has now landed on the destination point, entering the trigger volume. But of course we need some kind of functionality that maintains when these boxes are on their destinations or not, because there will come a point during the game logic where we'll need to check when all the boxes are on their destinations so that we complete the level and move to the next one. So I want to handle that functionality now, and I'm going to do that by creating a new C# class specifically for the box class. So I'm going to stop playback here, switch over to the scripts tab, right click, choose create and choose C# script, and I'm going to call this script crate, like so. I'm going to double click to open this file in MonoDevelop, and we can see it here in MonoDevelop. And there's a whole range of code that I'm going to need to create for this. I'm just going to select all of this, press Ctrl V to paste in that code that we have here. So what I've done is I've created a Boolean property. B is on destination, and this begins as false. This value will be switched to true when the box is on the destination. And we have these 2 functions or events here, onTriggerStay and onTriggerExit. When the box is pushed inside the destination volume, and when it remains inside the destination, so when the box is pushed onto one of these targets inside its trigger volume, for as long as it remains in there, the onTriggerStay function will be called. When the box leaves the destination, onTriggerExit, then again this event will be called and we switched onDestination back to false. That should happen in case, for example, the user pushes the box onto the destination and then pushes it off again, where you need to be able to handle for that scenario. So I've got this cube here in the scene, and what I want to do is apply this crate script to that cube. So I'm going to click and drag the crate script onto this box here so we can see that in the scene. Now of course if I press play on the toolbar and I begin pushing the box, and again if we keep an eye on the object inspector here, we are expecting this on destination flag to enable when the box is pushed into this endpoint here, but you'll see that actually nothing happens. This tick is not enabled, and again if I come over to this side and I push the box off of the destination, again nothing changes. And the reason is because collisions can only be detected between these colliders and the trigger volumes if one of the collider objects has a rigid body controller, a rigid body component. So what I'm going to do is add a rigid body component to this box here. I'm going to move up to the file menu and choose component physics, and I'm going to choose rigid body. And now I've added a rigid body to this box. But now let's see what happens when I press play on the toolbar. Again, the box now, because it's using gravity and physics, it falls through the floor because we have no collider for the floor. But we can override all this default physics behavior by enabling this box here, by enabling this checkbox, is kinematic. That will disable the default physics handling and allow us to override it using our own functionality. So now I'm going to press play on the toolbar, push the box forward, keeping an eye on this value here, and then as I push the box onto the destination, suddenly now it is enabled. And if I go back to the other side of the box, like so, let's go around this side and push the box off the destination, now it is deactivated because the box is no longer on its destination. So right now it's really useful to have these crate values. We're not going to be processing them all just yet. Later in this course, we're going to be creating a game manager class that will search through all the boxes in the scene, making sure they're on their destinations to progress things to the next level. But we have this functionality built into the crate now for when we need it later. So what I'm going to do is switch to the Prefab tab, right click, choose Create and select New Prefab, and I'm going to select Create Prefab, and I'm going to drag and drop this box here onto the prefab just to create a new Create Prefab. I can switch out here now, of course, and start to drag and drop in the other boxes that we need for this level. And in doing that, we have completed the Create Prefab. Now in this final section for this part of the course, I want to consider camera functionality and the general chase view. Previously, I had selected the camera object in the scene and parented it to the game character, so that wherever the character went, the camera automatically followed. But right now I've unparented the camera, and if I press play on the toolbar and I move the character around, the camera simply doesn't follow at all because I've unparented it. Now, parenting the camera in that way and following the character worked fine, but still we can improve the general camera handling mechanics and the smoothness of the camera if we apply some scripting. Now it just so happens that Unity comes with a script built in that we can use to apply smooth camera following. We can access that by clicking on Assets from the File menu, Import Package, and we can import the scripts package which contains a script called Camera Follow. Now that script is coded in the JavaScript language. So what I've done off screen is I've created my own C# version of that script, of that implementation. In the scripts folder you'll see Camera Follow, and you'll see the C# version that I have created. So this is a C# alternative that I've created here, and what you can do is you can just drag and drop that onto your camera object. And when that's applied to the camera object, you will see that we have a Camera Follow component. And we can simply pass in here for this target field the object that we want to follow during the game. So I'm going to drag and drop the character object into the target field and press play on the toolbar. Now when I do that, you can see immediately we get some smooth motion with this camera and it's following the player object. But of course it really is quite some distance away. So we can decrease the distance here. We can maybe specify something like this. And maybe I don't want it to be so far above the character, so again I can change the height here, like so. I can control the height. And notice how when I change the height, it smoothly blends in there. It doesn't just zoom in a very discreet and rough way. Instead it's very smooth here. There's a lot of damping going on. So again I can rotate the character, and that's looking pretty good. Now I've actually got some values configured that I want to use here. I'm going to set the distance to 3, I'm going to set the height to 5, the height damping to 2, and the rotation damping to 10. Now let's press play on the toolbar, and when I do this you can now see we've got the sort of camera mechanics that we need for this game. So I can just push this box onto the destination point, I can walk over here, grab this box, and again the camera smoothly follows. Again, it's not parented to the game object, it's completely independent. So I can come out here, push this box onto the destination, walk over to this side, grab this box, again push that onto the destination. And now for the final box in the scene, and this will complete a level. Of course, have to turn it around here, turn around here, push this there, finally move this over here, and now for the last push of the game, and voila, one level completed. Of course right now it doesn't detect that. Of course if we view each of the targets in the scene, you'll see here, let's just find the crate actually, sorry. So the crate, again, this is on destination, on destination, on destination, and on destination. All 4 crates are on their destinations, and we've got a smooth following camera. So that really completes this section of the course. Thank you for watching. This has been 3D Motive. I hope you found this module helpful. Next, we're going to be considering particle systems and a whole lot more.